Hello everybody, getting ready to do lesson 10.4 part 1, pre-calculus math today, and 10.4 part 1, classwork, lines and planes in space. You will have 16 points on your notebook guide, and then 36 points on your classwork sheet. Have those out. Name, date, period. Okay, into page 1, lines in space. In the plane, slope is used to determine an equation of a line. In space, it is more convenient to use vectors to determine the equation of a line. So here's some lines here. Consider the line L, this line here, through the point P, so through this point here, and parallel to the vector, parallel to this vector down here, ABC, direction vector for L. So this is kind of like a direction vector here for L up here. The vector V, this one down here, is the direction vector for the line L, and A, B, and C are the direction numbers. So A, B, and C down here are your direction numbers. One way of describing the line L is to say that it consists of all points. Right here's your direction numbers, that it consists of all points Q, X, Y, Z, for which the vector PQ here, PQ, this vector here, is parallel to V. So one way of describing the line L is to say that it consists of all points Q, which include X, Y, and Z, for which the vector PQ is parallel to V. So PQ here is parallel to V. This means that the vector PQ is a scalar multiple of V, and you can write the vector PQ would equal TV in this case here. So vector the multiple of V, you can write vector PQ equals TV, where T is a scalar of vector PQ. So we have X minus X1, and we have Y minus Y1, Z minus Z1. And then AT, BT, and CT equals TV here. So A times T, B times T, and then C times T would be a way of describing this where T is a scalar of vector PQ. By equating corresponding components, you can obtain the parametric equations of a line in space. So this is why we have parametric equations, is that you can obtain a corresponding component for a specific line in space. Okay, well, let's get further into this. Parametric equations of a line in space. A line L parallel to the non-zero vector V equals A, B, and C. So a line L parallel to a non-zero vector V would be A, B, and C. And passing through the point P, so X1, Y1, Z1, is represented by parametric equations. X equals X1 plus AT, Y equals Y1 plus BT, and Z equals Z1 plus CT, A, B, and C. When the direction numbers A, B, and C are all non-zero, you can eliminate the parameter T to obtain the symmetric equations of a line. So here would be an example here of the symmetric equations of a line. X minus X1 over A, Y minus Y1 over B, and then Z minus Z1 over C. That'd be an example there of symmetric equations. Finding parametric and symmetric equations. Find parametric and symmetric equations of the line L that passes through the point 1, minus 2, negative 2, and then minus 4, and is parallel to V, which is 2, 4, and negative 4. Okay, so to find a set of parametric equations of the line, use the coordinates x1 equals 1, y1 equals negative 2, and then z1 equals 4. So in this case here, x1 equals 1, so x1 equals 1, which would be here. And then y1 equals negative 2, so y1 equals negative 2, which is over here. So c1 and then negative 2, and then that would be up here 1, negative 2, and 4, and then z1 equals 4. So that would be this plot here. So find a set of parametric equations of the lines, use these coordinates here. Okay, we got them. And direction numbers a, 2, 4, and negative 4. So in this situation here, we have, here's our direction numbers down here, 2, 4, and then negative 4. For our vector v is down here. Okay, having that, we can go x equals 1 plus 2t, and then y equals negative 2. Y would equal negative 2 plus 4t, and then z would equal 4 minus 4t. So 4 minus 4t, and then negative 2 plus 4t, negative 2 plus 4t, and then 1 plus 2t. In this situation here, 1 plus 2t. Because a, b, and c are all non-zero, a set of symmetric equations is, here we are, x minus 1 over 2, y plus 2 over 4, and then z minus 4 over negative 4. So these will be symmetric equations versus the parametric equations, which are up here. So let's try one. For these 7 through 12, a set of parametric equations, and b, if possible, a set of symmetric equations for the line through the point and parallel to the specified vector or line. So here's our point, and it's parallel to this line here. So our first step here is x equals x1 plus at, which is 0 plus t. So this is 1 times t, 0. So it'd be x1 would be 0 plus 1t, and then y would be y1 plus bt, so it'd be 0 plus 2t, and then z1 would be plus ct would be equal 0 plus 3t. So here are our parametric equations over here. So a set of parametric equations. So x equals t, when we solve this for x, we get x equals t, y equals 2t, and then z would equal 3t. Here's our parametrics. And then for b here, if possible, a set of symmetrics. So our symmetrics here would be x equals 1. So x equals 1 equals y over 2. And then z would be z over 3 would be our symmetrics for that. Okay, class, so down here I want you to do these on your own using this as your model. Okay, otherwise we're going to move on here, and we have neither the parametric equations nor the symmetric equations of a given line are unique. For instance, in example 1, by letting t equal 1 in the parametric equations, you would obtain a point 320. So if we in example 1, by letting t equal 1, you would get this 320 here in the parametrics. Using this point with the direction numbers, a equals 2, 4, and negative 4, a, b, and c, produces the parametric equations of x equals 3 plus t, 3 plus 2t, and then here y equals 2 plus 4t, and then z would just equal negative 4t. Parametric and symmetric equations of a line, so through 2 points. So find a set of parametric and symmetric equations of the line that passes through the points negative 2, 1, 0, and 1, 3, and 5. So begin by using the points p equals negative 2, 1, 0, and q equals 1, 3, 5. then a direction vector for the line passing through PQ is V equals vector PQ. And then we're going to do our direction vector here, 1 minus and negative 2, 1 minus and negative 2, 3 minus 1, and then 5 minus 0. So that's going to give us a 3, 2, 5. Here's our direction numbers here, A, B, C. After we find our direction vector, we have our direction numbers here. Okay, so now we have our direction numbers. Using the direction numbers, A equals 3, B equals 2, and C equals 5, with a point P of negative 2, 1, 0, you can obtain the parametric equations, and negative 2 plus 3t, and then 1 plus 2t, and then z would just equal 5t here. Here's our parametrics. And then because A, B, and C are all non-zero, a set of symmetric equations is x plus 2 over 3, so x plus 2 over 3, and then y minus 1 over 2, y minus 1 over 2, and then z over 5, z over 5 over here. We have a 0 here, so it'd just be z over 5. These would be our symmetric equations. Okay, so now let's try one. Find A, a set of parametrics, and B, if possible, a set of symmetrics for these 2 points here. So for up here, for 13, we're going to start out with this. So we have a direction vector here of negative 1, 4, negative 5. And this is through point 202 here. So we have a 202 and then 1, 4, negative 3 here. So A would be x equals 2 minus t. So it'll be 2 minus t, and then y would equal 4t here. So 2 minus t, and then z would equal 2 minus a 5t here. So that would be our first set, and then B here, that would be a parametric, and then our symmetrics would be x minus 2 over negative 1 equals y over 4, then z minus 2 over negative 5. This would be our symmetrics here. Planes in space. You have seen how an equation of a line in space can be obtained from a point on the line and a vector parallel to it. You will now see that an equation of a plane in space can be obtained from a point in the plane and a vector normal, meaning perpendicular to the plane, in a vector normal. So we have a situation here, NPQ. Consider the plane containing the point x1, y1, z1, where I don't see it in here, having a non-zero normal vector. So n would equal ABC. So this would be n here, be NBC here as shown. This plane consists of all points of Q, which would be x, y, z, which would be here, for which the vector PQ here is orthogonal to n. So PQ here is orthogonal. Here's your right angle here. So vector PQ is orthogonal to n. PQ is orthogonal here. Using the dot product, you can write the. So let's get into a dot product here. N times vector PQ equals 0, meaning ABC times our direction vector here will equal 0, is what that means. So A times x minus x1 plus B times y minus y1 plus C times z minus z1 equals 0. The third equation of the plane is said to be in standard form. This is standard form here, by the way. In a standard equation of a plane in space, the plane containing the point x1, y1, z1, and having non-zero normal vector n equals a, b, and c can be represented by the standard form of the equation of a plane. So a times a x1 minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. This is the standard form of the equation of a plane. Regrouping terms yields the general form of the equation of a plane in space. So we have ax plus by plus cz plus d equals 0. This is your general form of the equation of a plane. Given the general form of the equation of a plane, it is easy to find a normal vector to the plane. Use the coefficients of x and y and z to write n equals a, b, and c. Okay, that's all great. Finding an equation of a plane in 3 space. So, find a general equation of a plane passing through the points 2, 1, 1, 0, 4, 1, and negative 2, 1, and 4. So to find the equation of the plane, you need a point in the plane and a vector that is normal to the plane. There are 3 choices for the point, but no normal vector is given. To obtain a normal vector, use the cross product of vectors u and v extending from the point 2, 1, 1 to the points 0, 4, 1 and negative 2, 1, and 4. So negative 2, 1, and 4, and then 0, 4, 1 over here. Then here's 2, 1, 1 over here. The component forms of u and v are, u is between these two up here. The component forms of u and v are negative 2, 3, and 0. And then v would be negative 2. You combine these two together now, and you have negative 4, 0, and 3. So once we have those, n equals u times v. Here's our matrix here for that, which will come out to 9i plus 6j plus 12k here in this situation. And that's our ABC right here, 9, 6, and is normal to the given plane. Using the direction numbers 4n and the point x1, y1, z1, which is 2, 1, 1, you can determine an equation of the plane to be, here's our general form here, and then here's our plug-in. This is our standard form for the equation of a plane. And then once we do that, we end up with 9, 6, 12 minus 36 equals 0. And then when we simplify that out, we have 3x plus 2y plus 4z minus 12 equals 0. We factor out a 3 out of this. And then check that each of the 3 points satisfies the equations 3x plus 2y plus 4z minus 12 equals 0, which I'm sure they do. Now, let's go into our guided practice here. In these exercises, find the general form of the equation of the plane passing through these 3 points here. So here's our u, here's our v, and then we multiply these out here, and we end up with these direction vectors here, 1, 1, 4, and then negative 1, negative 4, and 2 for up here. And then, so now we can make our matrix here, and we 1, 1, and 4, which is here, then negative 1, negative 4, and 2 is here, and then this multiplies out as 18, negative 6, and negative 3, and then I'm going to let you do that one there. And that is 10.4 part 1 pre-calculus math. Here's my email for questions or materials for the course, animated PowerPoint math video at AOL.com. Thank you very much.